In the next section, we'll study another important parameter, which is the 95th percentile. So just to refresh our memories, the percentiles are related to the z-value as shown in this equation at the top. The percentile is mu g, that's the geometric mean, times sigma g raised to the power plus or minus sigma. And so the 95th percentile is given by mu g times sigma g raised to the power 1.645. And where z equal to 1.645 for the cumulative normal distribution. And so 95% of the exposures in this distribution are going to be less than the 95th percentile. That is the definition of the 95th percentile. Again, this is a point estimate with some associated uncertainty. So the 95th percentile is in the upper tail of the exposure profile, and we actually are very interested in it. And it turns out that this is our decision statistic when we are looking at reaching a decision about whether an exposure profile is considered controlled or acceptable or unacceptable, or falls in one of the AIHA categories that we talked about previously in this course. When we say something is a decision statistic, we are basically saying that this is the value that we are going to compare with the occupational exposure limit to determine whether an exposure profile is considered acceptable. Why are we looking at the 95th percentile to make this comparison and not, for example, the arithmetic mean or the geometric mean? The reason we want to compare the 95th percentile is that we want to protect almost all of the workers. And the 95th percentile is sufficiently at the upper end that we can say if the 95th percentile is less than the exposure limit, then we can say with a level of confidence that we can protect most of the workers, in this case 95% of the workers' exposures. If we had chosen to compare the geometric mean, for example, with the exposure limit, then if the geometric mean is less than the occupational exposure limit, then we are at best protecting 50% of our workers, or 50% of the workers' exposures. That is not the goal we want to achieve. We don't want to protect half of our workers. We want to protect most of our workers. And this 95th percentile interpretation of time-weighted average OELs is widely accepted by a variety of professional bodies and legal bodies. The AIHA, for example, has provided this interpretation for its own exposure assessment strategy. The employer should maintain a true group or individual upper percentile exposure less than the exposure limit. And they have defined as SEG, a similar exposure group, 95th percentile, should be less than the TWA OEL. And as long back as 1979, researchers such as Morton Korn, who also used to be an OSHA director, and Nerton Esman, very well-known professor, they have similarly interpreted the 95th percentile, that is, in fact, the appropriate decision statistic. NIOSH guidance also uses the same interpretation. OSHA also, since 1987, has used this particular interpretation. The ACGIH, or the American Conference of Governmental Industrial Hygienists, has also used this interpretation. And outside of the US, the EU, the European Union, also has documents that follow this particular interpretation. Okay, now let's get into the formula for the calculation of the 95th percentile. And I'm circling in red the formula for the 95th percentile. which is basically the exponent of the sum of the arithmetic mean of the log transformed values, that is the y bar, plus 1.645 times the standard deviation of the log transformed values. And you exponentiate it, and that becomes the 95th percentile. So let's use another quick example. So here we have just 6 measurements, and these are shown in the second column under xi, and the units here are in milligrams per cubic meter. And in the third column, we have the log transformed values of these measurements. So these are the yi. And at the bottom, you sum these log transformed values and you divide by the number of measurements, n, which is equal to 6 in this case, and you get a y bar of 0.062. And then you exponentiate it to get a geometric mean of 1.06. This is similar to the calculations we have done previously. Similarly, in the fourth column, you obtain the yi minus y bar. You square it, and then you take the sum of it, and then you divide it by n minus 1, and you take the square root of that, and then you exponentiate it, and you get a geometric standard deviation of 1.83. So this is all familiar to all of us by now. So the geometric mean is 1.06, and the geometric standard deviation is 1.83, again, with no units for the GSD. So now we have a sample of 6 full shift time weighted average measurements. In this case, it happens to be welding fume measurements, and we have calculated the GM, geometric mean, and the geometric standard deviation. So now our question is, what is our point estimate of the 95th percentile? We can use our formula here. The y bar was 0.062, and the standard deviation of the log transformed values was 0.6043. And so you can use this formula, and we can calculate a point estimate of the 95th percentile as 2.88 milligrams per cubic meter. An alternative way to calculate the 95th percentile, and this is a very convenient thing to remember, is the 95th percentile is just the geometric mean times the geometric standard deviation raised to the power 1.645. And so the geometric mean is 1.06, the GSD is 1.83, and you raise it to the power 1.645, and you get a value which is, again, 2.88 milligrams per cubic meter. Okay, now let's look at it pictorially. So we have our log normal distribution, and the geometric mean is 1.06, and you see where that is on the x-axis. It is very close to where the peak of the log normal distribution is, so around 1. The 95th percentile is a little bit farther away. It's 2.88. So we are around a factor of 3 away from the geometric mean.